We spent all this time talking about rich, lean, long-term fuel trim. Well, the oxygen sensors and the air fuel sensors are used to give us a signal of rich and lean conditions. We've got to verify the proper operation of these sensors before we go any further. And since fuel trim is totally dependent on oxygen sensors, we need to go into a detailed study of oxygen sensors and wideband fuel sensors as well, because they're on the newer vehicles. And to really understand wideband thoroughly, we need to understand the narrowband. Now, we're going to just call it narrowband, but they're really called inertial cell, which is just a technical term. We're looking at the operating range, and we're going to talk about a few things here. Let's first look at the voltage range. We have a voltage scale on the left that goes from 0, full lean, up to 1 volt, full rich, theoretically. Now, in reality, the ideal spot is in the middle, the stoichiometric. We'd really like to keep fuel mixture there, but it's impossible to do with this type of sensor. We'll show you why. At the bottom, we have our air-fuel ratio. In this narrow band, it goes from 14.3 to 15.1, but that's not our full operating range. The stoichiometric point is going to be very important for us later on. We're going to use that very, very important in the wideband. We're going to utilize that point later on, but it is the point that divides rich from lean. That's the important part about that. It's 0.45 volts. Now, the max indication for air-fuel ratio is a ratio of 14.4 to 1 air-fuel ratio. Now, we have a limit. The absolute bottom limit is 0.85 volts. We like to see them go over 0.9, and we frequently see them go to 1. So 0.85 is being generous. It's got to go that high. How do you get here? Snap the throttle. See if it goes all the way to 0.5, and then see if it goes full lean, because it should go full lean. Now, wherever it gets to the top, it flattens out, and once we pass 14.4, there's no longer any change in the oxygen sensor voltage. That's the max it can go. Now, when we go lean, it can go down to about 14.9 before it flattens out. Then there's very small changes. That's why we refer to this as a narrow band O2 sensor. A total range is going to be from 14.4 to 14.9. That's the usable range. That's very narrow compared to what we can see on the automobile doing normal operation. But it absolutely must cover the range of 0.1 volts lean and 0.85 volts full rich. So when we do our snap accelerate, it's got to go above 0.85 and drop down below 0.1, or it's not working properly. Yeah, we've got our middle portion and all that's important, and we're going to talk about the bias. But another thing that is a frequent failure is slow switching speeds. What should happen is this sensor should be able to switch between full rich and full lean in less than 100 milliseconds. We're talking about going this travel right here. What we normally see, if everything is working perfectly, driving down the road, it varies between 0.8 rich and 0.2 lean, steady throttle, idle, everything working properly. This is what it looks like on a scope pattern. Now, we have a full training course on this, and we encourage you to look at it. But look at the sine wave pattern. And if you go to the training course, you'll find out why we're rich a little of the time, why we're lean a little of the time, and what all this is about. We want to spend a lot of time on wideband. So we're going to shorten up this portion. But this is the signal you should see. When you rev up the engine RPM, you see it switching up to around 0.9, almost 1 volt in some cases, and down to about 0.1 at the bottom. That's normal for 2,000 RPM. But let's go back and talk about what can happen to this sensor. It can develop a bias. This example is a sensor with a rich bias that will cause fuel trim to be wrong. We will look at this, and because it thinks it spends most of its time rich, the fuel trim is going to be minus. It'll be low. It's very easy to go beat up on fuel trim. But as we've harped on so long in this program, short-term fuel trim is driven by the oxygen sensor. Long-term is driven by short-term staying wrong. What might happen in a case like this, where it fits in with misfire? If we had dirty injectors and they were unbalanced, and we had something shifted like this, causing mixture to be too lean, it's entirely possible that one of the injectors is a little dirtier than the others, a misfire code, and the vehicle does not think it's stuck rich or lean. It just has a bias. So it's changed long-term to reduce fuel. Means the car's leaned out. Our secondary ignition is going to be leaned out. It'll be all cylinders. We're going to be scratching our head. We're going to be beating up on fuel delivery. So pay attention to this. This really does have an effect on operation. A lean bias can cause a similar problem. Different symptoms, but here it wants to spend most of its time on the lean side. Now, we've had these cars, we know that carbon up all the time. What's going to happen here? Long-term fuel trim is going to be a high positive, trying to bring this back to the middle. As a result of that, we're going to be richer than we should be, and vehicles which are subject to making carbon build up are going to build up more carbon than normal. You see the pattern we're getting to here? Get to the root cause of some of these problems. Talk about mode 6 for a second. If you haven't used mode 6 data for oxygen sensor, you are missing something big. It's going to go through all the characteristics. Here's just a couple things it's going to measure. First, it's going to measure and give you a readout the max rich voltage and tell you what it is and what the spec is for that vehicle and how close it is to failing. Then it's going to tell you the max lean voltage and how close that is to failing. And it's going to tell you exactly where your threshold is. Our threshold is 0.45. That means the computer hasn't shifted around trying to fix for a system that's biased one way or the other. Then it's going to tell us about switching speed. It's going to tell us how fast the speed switches between max lean and max rich. In fact, it breaks it down even smaller. It'll tell you the switching time from rich to lean and from lean to rich, so you can see the bias. If it goes faster one way than the other, it has a bias. You can see the test results, and you can see the specifications it's used. You can't see this in scan data. It's only in mode 6. We really encourage you to go look at mode 6 because it should be making good, fast switching back and forth. Go look at that sensor, the mode 6 data on the oxygen sensor, and if you have a copy of it, pay attention to our oxygen sensor waveform diagnostics. It's hours of analyzing the waveforms. The next thing we need to look at is wideband air-fuel ratio construction. These are the newest sensors used to control fuel. They warm up much faster, they give us better information, and we'll show you why. But they're going to be utilizing the narrowband sensor. It interacts with the PCM just like the O2 sensor does. It samples exhaust gas like O2. It has a reference signal, which is going to be based on a narrowband cell. It's going to have the capability of changing current flow that will let us measure the air fuel more accurately than just the narrowband. Now, the current changes made to the sensor will be used by the PCM to use for fuel control very precisely, very fast, much better than narrowband. We're going to have to tell you all about it step by step. Let's take the time to look at the total range of air-fuel ratios we might find. And we're going to look to measure the different air-fuel ratio operating conditions. We look at our narrowband nurse cell there in yellow. It's right in the middle, occupying a very small portion. Notice the blue power curve at the top peaks out way down there around 13:1 air-fuel ratio. And we can't measure anywhere near there. And we can't measure fuel lean situations down at the bottom. Let's talk about why we'd want to measure this. For full power at wide open throttle acceleration, We need something about 13.2 to 1, somewhere in that range. A little richer sometimes, a little leaner depending on engine design. We need to have a fuel delivery system that can deliver fuel at this level, enough fuel to keep us at 13.2 to 1. If the fuel pump doesn't have enough capacity, you will find the mixture falls back. Now, we can't see that with a narrowband. That's why all your hot rod shops and your tuners go to wideband AFR sensors. Can we deliver fuel at this wide open throttle? This is a diagnostic. I cannot say it enough. You need to answer that question. Cold startup is going to need something in the same range. Do you have enough fuel? You're getting misfires when it's cold. If you are, you may want to look at the AirFuel ratio. And I know you get one with the narrowband cell, but it's not as accurate as what you get with wideband. If you're getting cold start information, says you're getting misfires in freeze frame when it's cold, you may have something out of calibration where you deliver too little fuel. Do you get full fuel shut off at 16.2 to 1 AFR? Do you have leaky injectors? Does it keep from getting down there? We can't see that lean with a narrowband cell. Wideband is going to cover the entire operating range. Everything we have here. It's going to be using a narrowband cell along with an O2 pump cell. Now, the O2 pump is going to pump oxygen in and out of a chamber, a sample chamber, where we can control what's in that sample chamber. We need to explain that to you because we've got to say it time and time again, because now life is fixed to get a little more complicated. What we have here is a shared electrode in the bottom. This big blue one, that's the electrode shared between the bottom narrow cell, and the top cell, and we'll talk about it. We have sandwiched two sensors together. The top is an oxygen pump. The bottom is a narrow-range oxygen sensor cell. What does the narrow range do? The narrow range clearly identifies when we're at stoichiometric, and the top is going to generate oxygen or pull out oxygen. We'll talk about that. But this is our common cell here. It's used by both the narrow range and the current pump. Use this same electrode. So let's go back and talk about what's going on here, about what we're going to be doing with this solid electrolyte nurse cell narrowband down here at the bottom. At the bottom, the narrowband sensor will respond to oxygen content of the green diffusion chamber. So our narrowband cell, the one down here, it's our standard cell we look at. It's going to be at 0.45 volts when it's a stoichiometric. All that theory is the same. It's mounted on the bottom. It's heated up by heater. Now, the diffusion chamber is made with a small air gap that limits the amount of exhaust gas up there in green that gets into the diffusion chamber. So what we're doing is we're making a chamber that only samples a little bit of the exhaust. The bottom narrowband tells us if this is far away or close to stoichiometric. If it says we're stoichiometric, nothing happens. So we're looking for the narrowband to have an output of 0.45 volts. That says the air in the diffusion chamber is at stoichiometric. Everything is happy. The car is running perfect. But we know that cars never stay at stoichiometric. So what happens when it's not at stoichiometric? When the chamber is outside of stoichiometric, something has to change because the fuel mixture is no longer ideal. Keep in mind, it can be outside of stoichiometric because we're accelerating, we're deaccelerating. We're not judging what the car is doing yet. Right now, we're just judging is the mixture at stoichiometric. There are times we do not want it to be at stoichiometric. We're going to use those times to measure wide open throttle, like we just talked about. But we are going to say now, how do we measure how close or how far we are? How can we get this wideband action out of this little narrowband sensor at the bottom? Well, we're going to do it with an oxygen sensor pump. If we're only allowing a small amount in, we have an oxygen sensor pump. It's that shared cell in the bottom with blue. We got that blue cell on top. Now what happens with this? It's a standard narrowband cell, but something unusual happens to narrowband oxygen sensors. If you drive current in and out of them, they will absorb and release oxygen. Yeah, we've always used it to let oxygen generate a voltage. Now we're using it in a different manner. Since we have a very small sample, we can change the oxygen content pretty easy. Why do we want to do that? Well, we're going to use this oxygen sensor pump in here to make changes. So this top sensor, it's going to pull oxygen out of the diffusion chamber if we are lean. It's going to pump oxygen into the chamber if we're rich. Why are we pumping oxygen in if we're rich? Because there's too little oxygen. And when there's a low stoichiometric, we won't get our 0.45 volts out of the bottom sensor. But if we pump just the right amount of oxygen in, we'll bring it back to stoichiometric and we'll have our 0.45 volts. If we're lean, we reverse the current flow and we pull oxygen out. We absorb the oxygen. This is the whole principle of operation. We pull a little oxygen out. Now let's go through and see that step by step. This diffusion chamber is made with a very small diffusion gap. We say that again and again because you need to concentrate. We cannot change the entire flow of the exhaust gas. We can't control that. We're going to have to use the PCM, long-term fuel trim, and vehicle operation to control what's in the exhaust gas. But this small sample going to a small sample chamber, diffusion chamber as it's properly called, we can control that environment. Let's see how we do that. It drives current through the O2 sensor at the top to create an oxygen pump. We're going to come right here. We're going to drive current in. The pump absorbs O2 with positive current flow passed through the top sensor. You see us pumping it in. This is because the PCM determined that the sample in this chamber is too lean. It has high O2. To bring that chamber back to stoichiometric, and when we get there, the bottom earth short-term reference, whatever you want to call it, voltage will be back at 0.45 volts. So we're pulling oxygen out. It's a small chamber, small sample. Maybe we're measuring deceleration. It doesn't matter why it's lean or rich right now. We're going to talk about what happens later when we go to controlling things. Well, what happens if we're going the opposite direction? When we're rich, the pump is going to release O2 by passing a negative current through the top earth cell, and it's going to create oxygen. Doing this because the PCM has determined the gas sample is rich, has low oxygen sample. Now remind you, it's a small chamber, it's got a very small amount of sample gas. So we can control the mixture in this chamber with our pump. How do we know when we're done? How do we know we have enough oxygen pumped in? We will know because the bottom narrowband oxygen sensor will read 0.45 volts, indicating we are now at stoichiometric. So the amount of current will tell the PCM just how rich we were. So now you've got the picture. We're going to pump oxygen in and out until we bring the bottom narrowband back to stoichiometric. And the amount of current flow is going to tell us where we are. Now, what action we take with this information is determined by, is this an offset in fuel delivery? If it is, we're going to change long-term fuel trim to make this correction. But if, for instance, we're at wide open throttle now, it's simply going to report to us what the actual air-fuel ratio is at wide open throttle. And that's something we want to measure. So the action the computer takes, the PCM takes, is depending on operating conditions. But that's the same thing we've been saying about oxygen sensors. Where people get confused is they say, well, if it's corrected it, what do I do now? Well, why did it correct it? Well, it's correcting to make a measurement. Once we made this correction, we're at 0.45 volts. We know exactly how rich in air fuel we are. Now, the next question, going back to long-term, short-term, is do we want to make a long-term, short-term fuel trim, or is this a normal operating condition? Don't confuse that. This process is the measurement process. The PCM is going to determine what to do about this air-fuel ratio. Let's look at this now in some other formats. So here's what's happened. Let's make sure we understand it. The pump at the top is pumping stuff in and out of the diffusion chamber. It's trying to control the air-fuel ratio in the chamber. And it's doing this as the PCM looks at the reference voltage at 0.45 volts on the bottom O2 sensor. When it reaches 0.45 volts, we have the right air-fuel mixture in the reference chamber, in the diffusion chamber. The amount of current, negative or positive, tells the PCM how rich or how lean we are in a wide range of air-fuel ratios. So what we've done is take two narrowband cells, hook them together in such a specialized way that one becomes a current pump and one becomes a reference. The reference tells us when we pumped in or pulled out enough oxygen. Then the PCM is going to determine what to do with that information. So let's go back and look at what we're talking about here. We got exhaust gas coming in. It's changing. If the mixture is wrong, then the short-term, long-term fuel trim is going to change it. It's going to say, oh, we see what's coming into the chamber. We've got to make changes. The closed-loop system is going to take over. This is exactly what we're expecting to see happen. We want to see mixture changing as we do different things for vehicle operation. We want to see lean or rich conditions that are caused by fuel delivery or fuel control be corrected with long-term, short-term fuel trim. So these two numbers at the bottom are going to change the composition of the exhaust gas when the PCM is determined it needs to be changed. They're going to report the actual value of the exhaust gas when it's information the PCM wants to know that we're going full rich, full lean, and we're supposed to be there. If we're rich or lean in the exhaust gas, comes into the sample chamber, we pump in or pull out oxygen, bring it back to reference, we now have the information we need to take what action should be taken. So let's look at what it looks like on a chart. We've seen those pictures. Now this, I don't know what color it is, purple. I think they say it's magenta, like here. We're going to pass a negative current through the oxygen when the mixture is rich. It has very little oxygen, and we're going to generate oxygen to bring that sample cell, diffusion cell, back to a 0.45 volt reference. So here's our low AFR. Here's our negative voltage. We're going to go down to 1.5 minus 1.5 milliamps. We're going to correct this 0.8 lambda back to 0.45 volts, 0 lambda at the bottom with minus 1.5 milliamps. So keep in mind, this is what it's going to take to bring this wrong mixture back to normal. Let's look at what we're talking about here. Here's our current milliamp. As we make correction, as long-term fuel trim changes, if it's out of order, it's going to bring it back to 0 milliamps as we come back to a lambda of 1. That's the normal action. If we had had too much fuel, we would have slowly brought it back by changing short-term and long-term fuel trim. Let's look at this again. Because this diffusion gap is small, we will take a small amount of oxygen to return the diffusion chamber to a stoichiometric. The amount of current tells the PCM exactly what the content of the exhaust gas is. We're trying to tie all this together for you. So what it's going to do, the current flow will be back to 0 after PCM has corrected fuel control. Fuel trim has corrected fuel delivery. Or we have changed operating conditions to where the vehicle is now back at a normal air-fuel ratio. This can get to be confusing because people say, how can you do this? Lean operation. Let's go to the other side, look at this, and then go look at a chart. The current pump will absorb, take out O2 when a positive current is passed through it to correct for a lean condition. And you say the same thing for the umpteenth time. The diffusion gap is small. Giving a small sample in the diffusion chamber, it's easy to control the mixture to get an ideal control. Let's see how we're going to do this. Here's our current. We're out here at lambda. PCM says, wow, lambda's way out here. I've got to change current flow in the diffusion chamber. So what it's going to do is it's going to bring current up to 2 milliamps. At 2 milliamps, it will absorb all of the excess oxygen created by a lambda of 1.8. Now, let me say that again. 2 milliamp will pull all the oxygen out of the diffusion chamber necessary to bring this 1.8 lambda in the exhaust back to stoichiometric in the diffusion chamber. Now, once it's corrected, let's look at this. PCM is going to decrease the current flow as fuel trim or operating conditions, whichever is taking place, because either fuel trim or operating conditions can put us in this condition. As we correct it, it's going to slowly bring both of them back. Maybe we've been doing a decel and we start accelerating again. Just to confirm what we know. Operating conditions, we change fuel trim to we change the exhaust. Do not think the oxygen pump can change the exhaust mixture. It doesn't. The pump merely decreases or increases current flow to generate small amounts of oxygen for the small diffusion chamber. It is PCM and brings air-fuel ratio back where it belongs. And remember, as we said, maybe it didn't bring it back because it was wrong. Maybe it brought it back because we had been doing decel. So we're going to be taking some test drives later on with a Toyota to show you how this works. And we'll show you exactly. There we'll be looking at voltages and how they change. But this is a good example of exactly how the current pump, how long-term fuel trim, how vehicle operations all work together to vary current flow depending on the mixture in the exhaust. We're going to change the very small sample in the diffusion cell and answer the question, what is the current air-fuel ratio? This is the basis of the narrowband. It's basically simple if you don't overcomplicate it. It can be overcomplicated easily, but it's all about bringing this sample cell, this small diffusion sample, that's only a small sample, into the diffusion chamber where we can control the lambda by varying current flow. Now let's talk about what is the normal range of current flow going to be seeing. Normal range of current flow ranges from minus 1.8 milliamps to plus 2.5 milliamps to measure exhaust air-fuel ratio. Let's say that again, to measure air-fuel exhaust. We don't use that to change the exhaust content. We use this current to measure the exhaust by controlling that light green diffusion chamber to an ideal mixture, to stoichiometric. The pump is going to be changing plus or minus, and we can see that. Let's talk about some actual application. First of all, we've got to make differences for manufacturing tolerance. We have anywhere from 300 to 30 ohm resistors somewhere in there used on this one sample. It's called a calibration resistor. It's going to correct for any minor differences in the manufacturing process. The big and most important thing about this, all the other stuff was good, but it ain't going to work without the heater. This heater is very important because exhaust temperature varies widely with engine speed and load, but the sensor requires a very stable temperature for measurement accuracy. We can't let temperature vary very much. It's got to be pretty precise. A high current heater is used. In this example of a Bosch heater, the current is in a range of 6.5 amps. It's a 10-watt heater. It varies from 2.1 ohms cold to 3.2 ohms hot, but it's going to try to maintain a temperature. The operating temperature ideally is 1400, but it's going to range between 13 and 1500. Now the heater is going to be designed to bring this up to temperature quickly. It's going to use a duty cycle controller on the current flow to maintain the correct value, which will give us the ideal 1400 degree temperature. This is built right into the wideband sensor. The new generation is made so that it can heat up in less than 20 seconds. Be operational, which means we can now have air-fuel ratio control at very cold operating temperatures. Why would you want to do that, you say? Well, if we want a 6 or 7 or 8 or 10 to 1 air-fuel ratio for cold operating conditions, we can now measure to see if that's what we're getting, not just assume it. So this wide range adds a whole new dimension to scan data diagnostics. We can read wide open throttle enrichment. We can read cold startup enrichment. We can get an entire range of information. Let's get down to looking at the pinout. Now we got a couple pins that we're not going to talk about. Pin 8, which is not shown, is a shield around all the wiring. We don't want anything interfering with this, any noise. Pin 7 on this particular Bosch is not used. Now let's start with pin 1. Pin 1 is the common output for the upper and lower cell. They're both narrowband cells. The bottom one is a true nurse cell. The top one is used as a current pump. Pin 2 is the voltage we're applying to the top current pump to generate or absorb oxygen to bring our diffusion cell back into stoichiometry. And 3 is heater ground. Very critical because the heater must be working properly. 4 up at the top is our calibration resistor. And 5 is our reference voltage. This is the voltage we're trying to hold at 0.45 volts. We're going to be running current in and out of pin 2 to keep pin 5 at 0.45 volts. Pin 6 is the other heater plus side, the battery power, B plus for the heater. Duty cycle to maintain the correct temperature. Yes, you can put a low amps probe and look at this. Good idea. But let's take a look at something slightly different. Toyota does not use an 8-wire connector like the Bosch. It does the same thing, but does it slightly different. It is built with 2 amplifiers being fed reference voltage. We have a 3.0 volt reference and a 3.3 volt reference. They're used on 2 balanced amplifiers. The top amplifier sets the voltage on the top of the sensor
at 3.3 volts.
The bottom one sets the bottom amplifier sets voltage in the bottom of the sensor at 3 volts. Now what's going to happen to these two is these two voltage will look like they're maintaining constant values because the amplifier is going to be changing it to make it a constant voltage. But it's going to vary current flow to keep those two voltages the same. Current flow through here, the 2 amplifiers, will be 0, no current, when we have a lambda of 1. Just like we had with the Bosch. We're pumping current in, pumping current out. These are showing us how we're pumping current in and out. The current flow through the 2 amplifiers will be positive with a lean mixture, meaning we're going to be absorbing oxygen, and it's going to be negative with a rich mixture, meaning we're going to be creating oxygen. It's going to work exactly the same way, only we don't have a 0.45 reference voltage we can see externally like we could on the Bosch. We can't see that 0.45 volts. We can only see the current flow. And bigger than that, the voltages remain constant. So if we really want to see it, the PCM changes, and the analog, the digital converter, changes this current flow into a voltage that represents AFR values internally to the PCM.
Now, because this is such a high-tech device, everybody's looking for some special, super high-tech way to test it. Well, here it is, the scan tool. My opinion, whether you have a Bosch-type system or this Toyota, they're both going to respond in scan data. Let's go look at our Toyota scan data, and you'll see what we're talking about. Scan data reads 3.3 volts. It's up and down. It's moving around a little bit. What we're going to do is we're going to do 2 snap accelerates. One quick one and one real hard one. We're going to analyze this second one because I want to show you what happens. It happens in both of them. The instant we hit wide open throttle, the first thing that happens is momentarily the mixture goes lean. When the mixture goes lean, the air-fuel ratio goes up, positive. Says we're pulling oxygen out of this diffusion chamber because there's too much coming out in the exhaust. Why is there too much in the exhaust? Because it's supposed to be lean. We're going to go wide open throttle. Now, if immediately after we go wide open throttle and it leans out momentarily, it goes down to the rich side. Now we have a negative signal, lower, it's 2.7 volts, pumping oxygen into. We were pulling oxygen out. Now we're pumping oxygen into. What this is doing now is pumping oxygen into the diffusion chamber because the operating conditions of the vehicle
is we're rich. Remember, this is something we wanted to see. We wanted to see full rich. Let's look at how this whole thing operates. Once we take our foot back off the accelerator, we're going to decel, and it's going to go boom, up full lean. We can see as much as 5 volts on some vehicles. Then, after it settles down, it comes back to the middle and gets back to the middle. So that's what's really happening. We can watch this in scan data, so why make it hard? By the way, you may want to learn how to do grafting if you don't already do it with your scan tool. But our full rich is showing normal reaction to acceleration. It is enrichment. It's supposed to be at 2.7 volts. That 2.7 volts means it's drawing enough current to bring our diffusion cell back to stoichiometric. Full lean, we're going to be pulling oxygen out. It's going to take 3.8 to 5 volts, depending on the vehicle, how new it is, to pull excess oxygen out so we got the diffusion cell back to 0.45 volts. Remember, we're not changing the exhaust. We're only changing that small diffusion cell with a small diffusion gap. So what you've seen now is fuel delivery, fuel control diagnostics with wide open. We've used the Toyota scan graphs to determine that the system is fueling correctly. Short-term, long-term fuel trims are going to result from the AFR signal just like they did with the oxygen sensor. Use them both to determine rich and lean conditions. It doesn't matter which ones we're using. They both work equally well for us. Normal steady throttle, yes, 3.3 volts. When we accelerate, it goes momentarily lean and then goes full rich. This is the test drive. Lambda now is equal to 0.9. That's saying we get full fueling. And look, it stays down there. We're getting enough fuel. We can go for test drives. We can do real diagnostics. When we're holding a lambda of 0.9, that means we've got full fuel flow from our fuel pump. We're able to give us what we're expecting. Rich limit for narrowband is 14.4. We could not have seen that. But an AFR sensor, we can actually measure the wide open throttle fuel delivery. This is why it's more benefit to us than the narrowband fuel nerve cell. Fuel delivery, all being correct fuel trim by looking at fuel PIDs. Each PID tells us a specification as well as an actual engine condition. We looked at PIDs when we're doing wide open throttle to see if we're getting proper fuel. We looked at long-term fuel trim to see if we're getting the proper fuel control. Was it varying to match operating conditions? Was it correcting for fuel delivery problems by changing long-term, short-term fuel trim when we have mechanical components? But we've done all of this by utilizing the marriage between all the sensors and the scan data so we understand it totally. Fuel delivery. To check for fuel delivery, you're going to have to go into scan data, make sure it indicates normal fuel control. Critical things to remember. Fuel delivery is more demanding at wide open throttle. It's harder to deliver high volumes of fuel. Pressure must be normal under all operating conditions that match the operating conditions. And the other thing to remember is injectors don't become equally dirty. Some are more dirty than others, and you may wind up with a lean operating condition setting a misfire code caused by lean mixture. And some injector cleaner solvents can damage fuel pressure regulators. We've run into a great deal of that the last few months. So now let's go look at fuel delivery, the mechanical side of this,